Welcome to the 2015 NASA Ames Summer Series. Modular design reduces risk and speeds up technology advancements. Also, combining capabilities from different fields leads to disruptive evolution of technology. So the combination of modular design and looking at different fields in combination really advances whatever technology we're looking at. Today's talk, entitled Affordable Airplanes, Modular Design and Additive Manufacturing, will be given by Kevin Reynolds. Kevin received a dual bachelor's degrees in physics and mathematics with a minor in electronics from Norfolk State University. He then went on to get the master's degree, and as you could guess, he did a dual master's degree in aeronautics and mechanical engineering from Stanford. He's both an NSF and a Stanford Graduate School Business Insight Program Fellow. Along the way, he's had many experiences. He's worked at CERN in Switzerland, BMW Technology in Germany, Hitachi in Japan, and Golden Key International in China. He came to NASA Ames in 2010 and as a civil servant as an aerospace engineer in the Intelligence System Division. He has won numerous awards, and obviously he has won the NASA Ames Early Career Research Award that my office handles. So please join me in welcoming Kevin Reynolds.
Thank you. Thank you for the introduction, and it's a pleasure for me to have the opportunity today to present to you on a topic that I find extremely fascinating, and that is of using 3D printing to make airplanes. So as you can see, the title is Affordable Airplanes, Modular Design, and Additive Manufacturing. I want to start just by focusing on the word affordable, because it's somewhat misleading in that everyone has their own perception of what is affordable. And that perception changes as we go through our lifetime. So instead of this talk focusing on actually placing a value, a dollar value, on affordable airplanes, we're really going to focus on the value proposition that can be offered by two key design elements. And those elements are modular design and additive manufacturing, also known as 3D printing. This talk is focused on demonstrating the use of those design elements for unmanned aircraft, but may have future applications for other type of airplanes that are designed to different requirements. I want to also acknowledge and thank the contributors of this work. The success of the project was built on the shoulders of giants, as they say, and so credit is given to the team that made this happen, as well as the advisors and the mentors that indirectly or directly influenced the work here. Matt Fladlin, Dr. Don Nguyen, Dr. Bob Dahlgren, and others, many others. So I wanted to start by framing the talk with an experience that I had as an early engineer. In fact, I was actually a physics major at the time, and I visited a place called the Pima Air and Space Museum. This place is in the middle of the desert in a place called Tucson, Arizona, and this is where airplanes go to die. So at the end of a lifetime, which is usually determined by when the materials in the aircraft have reached a fatigue point where they're no longer deemed airworthy, they are taken to this place, and the low humidity in the desert preserves the part so that it can then perhaps be reused in certain applications. But here in the middle of the desert, there are over 4,000 airplanes that are just sitting, waiting for the possibility of having a part here or there salvaged or repurposed for a new airplane. The engines, obviously, are usually taken off first and overhauled. But this really points to a big problem that the aerospace industry is facing, and that is how can we extend the useful lifetime of aircraft so that by reusing parts, by taking surplus parts and repurposing them so that we don't have all of this waste. Because this was my first experience when I was an undergraduate visiting this place, but 15 years later, I think of this place and I think this is the worst place in the world for an aerospace engineer, because who wants to design an airplane that will sit in the desert for 20 years? Well, design an airplane and then have that airplane sit in the middle of the desert. And so this is really what helps to frame the rest of the discussion today. So I look for places for inspiration in many different places, but one of the unlikely places that I found the inspiration was actually my 4-year-old son. His name is Arlo, and he aspires one day to be an astronaut. And he loves playing with Legos, and most of us are familiar with Lego design. But the idea of Lego design is that you can take very simple components and rearrange them and reorient them in ways that will produce a new product. Sometimes that product can be bigger than the person actually creating it. To the right, he is using his imagination to show what he would look like as an astronaut. So this really encouraged me to think, are there things that I can do to possibly optimize a process for making an airplane so that we can extend the useful life of that airplane and make it and reduce the waste associated with these airplanes. So one of the processes that I want to focus on is of additive manufacturing, also known as 3D printing. And the process of 3D printing is that you can take a CAD drawing, a virtual shape, and you can create a three-dimensional object by depositing layers on top of one another. And the different methods that are used differentiate between the different types of printers used for this method. But we want to leverage this in some way in order to repurpose some of the existing parts of these airplanes. So the innovation lies in the idea that from an amorphous design space, we can then start creating designs that are optimized specifically for meeting mission requirements. And the two fundamental elements are the modular design and additive manufacturing. The advantage of modular design is that we intentionally design an airplane so that the parts can be interchanged, and we can update the design as the technology matures and as it advances. The main advantages of additive manufacturing are that you can print and realize a part on demand without having to wait for something to be shipped to you. And this can have huge impact on mission requirements that may be in remote locations and other specific situations such as that. But the real advantage is in reducing the development time, which can then translate into development cost for the specific application. So high-performance airplanes represent a big opportunity for reducing overall cost. You can think of the vertical axis being the sticker price of an airplane. We also call it the acquisition cost. And traditionally, that acquisition cost is a function of how high-performing the airplane is. And we usually tend to use a metric called endurance to describe the performance of an unmanned vehicle that could be used for a NASA mission. So the longer time that airplane can fly, and usually the bigger the airplane is, the higher the acquisition cost. But what we really want to focus on is how to make this relationship more or less linear as opposed to exponential as we see in the plot. So we want to illustrate some of the concepts specifically of modular design and additive manufacturing using an existing design that many of you have seen on the way in called the Franken-Eye design. And we want to also extract potential lessons learned for future applications. So we've talked a little bit about the motivation, so let's dive into the modular design aspect. So Earth science missions here at NASA are really a core competency that we have relative to other NASA centers. And Earth science missions really focus on taking unmanned aircraft or even manned aircraft and flying them to parts of the world that we want to better understand. And one of the places that we want to better understand are volcanoes. This is a picture that was taken from Turrialba volcano in 2003, which is located in Costa Rica. And the scientists were very interested in understanding what type of gases were being emitted from the volcano and how that might impact climate change, for instance. But what we found out very quickly was that when we took parts that were surplus from as military hardware, those airplanes were not optimized for the long endurance that we wanted in our science missions. Science missions also tend to want aircraft that will carry large payloads, large sensors, and fly those sensors for long periods of time. We didn't have that in the current design. So this raises the question, how can we optimize, how can we modify an existing design so that we can meet the performance requirements for the specific mission? So one of the ways that we wanted to leverage technology was through the use of additive manufacturing. And this illustration compares the subtractive manufacturing process to the additive manufacturing process. Typically in a subtractive manufacturing process, you start with the material and your design is largely constrained by what you can manufacture with that material. Carbon fiber, for instance, needs an autoclave to solidify the part. And so because of those type of limitations, we also are limited in terms of the final assembly that we hope to achieve. Additive manufacturing, on the other end, really allows you at the very early stages of the design to focus on the functionality without being limited directly by the material choice. And so we can generate parts that can then be sent to a printer, and we can decide on the materials based on the requirements that we have. So for this project, we wanted to take advantage of the fact that we had a good number of surplus UAVs that had been provided to us by the U.S. Marines, and the feedstock that we had for this specific project was the Dragon Eye UAV, which is also here with me. This aircraft is designed in 5 pieces, and those 5 pieces can be detached from the aircraft. So you can simply snap the wings off, which are being held together using bungee cords. And this is really nice because if you hit a tree or if you hit the ground or you hit something else, then you can absorb the energy in the joint instead of having it break apart that would need to be repaired. So because of the design of this airplane, we wanted to leverage the fact that we had a modular wing, we had a modular payload compartment, which tends to be the nose cone, and we wanted to build off of that by using 3D printing to create new parts that would enhance the performance of the existing design. So the 5 parts are shown here, the 2 wing modules and a center wing pod that holds the battery, and then the tail and the nose are those components. And this design is such that it can be assembled in less than 5 minutes for the purposes of a typical mission. So to demonstrate this concept, we took several Dragon Eye UAVs and the components that they consisted of, and we looked at ways of rearranging them or reorienting them in a way that would improve performance. In general, a long, slender wing will provide the longest endurance for an aircraft. And so this is an example of an aircraft where we attempted to print essentially every part of the aircraft, including the wing sections, the structural components as well, the nose cones and propeller blades. And this is just to demonstrate the vast variety of parts that we could achieve using 3D printing, with really there being limited material constraints for producing a given part. And so you can think of this design as being a function of how many units are attached together. And so you can think of this as being a 3U design, similar to the jargon that's used in small satellite design. And so what we really want in the earth science community is something that looks like this. This is the Helios aircraft, which was actually a joint project between NASA and several other government agencies. But it was an extremely high-performance aircraft. The caveat, though, was that this airplane wasn't designed for cost. And so could we replicate something with a similar performance, but with a lower cost point? So as some of you may know, the Helios did crash a few years back, and it was attributed to some difficulties managing the flexibility of the wing associated with the Helios and how that flexibility was accounted for in the control system. Now we have tools that allow us to model the flexibility of the materials as well as the contributions of the propulsion to the design. And so going forward, we could look at designs like this. This is a 16U design, which we have the capability to model. So when you actually look at the performance contributions of these individual elements, you can then start to understand how each component is contributing to the overall performance. And normally when we use endurance as the metric for performance, we can look at aerodynamic efficiency, propulsive efficiency, and structural efficiency. This focus is really on the propulsive efficiency and the aerodynamic efficiency of the design and the different contributions. In general, when you take a propeller and you have it blow across a wing, it increases the dynamic pressure on the wing and thereby increases the lift capacity of the wing. But the trait is that it also contributes to drag. So by making these important traits and choosing an optimal wingspan, we can establish the trait between aerodynamic efficiency and propulsive efficiency, which both feed into endurance, which is what we're interested in. So say we wanted to design an airplane that was optimized for a specific mission. So we could choose certain parameters which we choose to optimize for. Maybe in this case it would be maximum range and with other constraints on climb rate and other things. And then we can start to generate trajectories that look something like this, where we're looking at the blue line represents the trajectory that the aircraft would take from in the vertical plane, and the green line represents the speed at which that airplane would fly. And so one thing that we understand very quickly, specifically with this battery-powered design, is that speed optimal flight is extremely important because it's a hit or a miss on the aerodynamic efficiency of the design. And so this is just an example of how, by understanding how those different parameters feed into the mission, you can then start to optimize for things like maximum energy recovery in the descent of the aircraft. So we talked a bit about modular design. Now we want to talk more about additive manufacturing and the contributions it can potentially make to the structural efficiency of a design. So this is a drawing that was taken of the first powered flight here in the US by the Wright brothers. And the unusual thing about this design was that it didn't come together with aerospace grade materials. It actually came together with wires, cloth, and wood, things that you typically wouldn't think go inside of an airplane. But one of the things that we know that they understood was how to make lightweight structures using those materials. And they had to overcome the challenges of the propulsion and of the aerodynamics by making extremely lightweight parts. The reason why this is an interesting example is because that same lattice structure now feeds into some of the lightest weight structures that we know exist today. This was a structure that was manufactured using a similar 3D printing method, but then electroplated in metal, and it's shown sitting on top of a dandelion, extremely lightweight, but was manufactured using a very similar method. So the point of me showing this is really that this captures the story of innovation and why innovation is so important, because as materials change, as technologies change, those allow us to then innovate in ways that weren't possible 5 years ago or 10 years ago or 20 years ago. So in order to kind of further extend the concept that we presented with the Frank and I, we invited several students and personnel from many different backgrounds, male, female, white, black, and young and old, Republican, Democrat. I guess I got carried away there. But we invited several students, young engineers, to experiment with the advantages that we could potentially see using these methods. And so we formed teams of 3, which were given the task of designing their own airplane to image in highest definition an object that we were going to place on the ground using their airplane. And the interesting thing about the result of those experiments was that they came up with 3 different airplane designs that were really designed to do the same mission. So this goes to say that many times we limit the design space to the point where we don't even consider ideas outside the box that may accomplish the same exact mission but in a different way. The first concept, which is shown here by Team Hyperion, was designed to enter into a hover, and once it reached a position where it was in the vicinity of the image that was the object being imaged, it would, from that hover position, create a 360-degree map with increasing the likelihood of it catching a high definition image of the object. And Team Chimera and Team Alicanto, they also looked at ways of extending the performance of the fixed-wing aircraft by adding winglets and enhancing the flap system. But this all shows that from a library of parts which we created for the students, there is an exponential design space that can be explored. and maybe some designs like the 1910 Jacobs design are possible. The next step of our summer task was to have the students simulate how their airplane would perform in an actual mission. And so they simulated cruise, they simulated hover, they simulated maneuver conditions that would place unusual asymmetric loads on the wing. They also simulated gimbal camera systems for capturing images from the stationary platform of the aircraft. And they also simulated high-performance, high-lift systems like the cambered flap system, which is shown here. And so through those simulations, they gained a better understanding of how these parts would ideally perform in the real world after being manufactured. So with the results of those simulations, they then went to hardware in the loop testing. This is an example of testing that was done on a flap system that you saw. And we had some of the students hook their autopilot to the hardware and actually, for the first time, really see that their design was actually working. And so they're doing some flap tests here, and they also do some power on tests. You can see the motor spinning to make sure that everything checks out in terms of the power system on the aircraft. So from that stage, we understood that the basic design worked, but we then needed to optimize them for structural weight and for other performance metrics. And so this is really where the skill set of the students came in, where they were able to apply their background in aerodynamics, structures, and other areas to optimize the design. And really what we want is designs that look more like what we see in nature. A bird's wing looks very interesting in that there's only material where it needs to be in order to maintain the certain load that the bird is carrying in flight. And we can also think about this, how this can be applied on the scale of the aircraft itself, using flexible materials, using shape-changing materials that would move us closer towards the direction of what we see in bird flight. Another area that we wanted to explore was how to take a cheap part that is printed in plastic or in some inexpensive material and to enhance the strength of that part. And we looked at two different methods. One is plating on plastic, curing on plastic. Plating on plastic is also known as electroplating, and it's widely used in the jewelry industry, in the plumbing industry, and many other industries, but is now being investigated for use in the aerospace engineering industry. And we also were looking at ways of taking carbon fiber, fiberglass, Kevlar, and using them to mold against a 3D printed part. The results of that were that we showed, using these different prototypes that are shown, that we could enhance the strength of the part by at least 3 times, making those parts almost comparable to the strength of aluminum, which is really impressive for something that costs roughly half the cost of an extruded piece of aluminum of the same dimension and shape. Another consideration that we would need to make in order to satisfy a mission requirement is understanding how the sensors play into that mission and how perhaps they can be optimized to collect the information that is important for the mission succeeding. And by having a variety of sensors, which are then themselves designed modular to the aircraft, we can interchange sensors to meet a certain requirement. So we talked about modular design, additive manufacturing, and now we can talk more about the specific missions and the flight operations that are required for getting the airplane into the actual mission. So the airworthiness process requires that we take parts and we test them to their structural failure point to better understand the limitations of the materials. And we want to make sure that the strength of the part begins to reflect the harsh environment that we expect to see in certain flight conditions. And so as a part of that airworthiness review process, we did static testing, which is where you take a wing and you load it to the point where it strains, and then you look for the place where it fails, and you try to understand something about why it failed, and look at ways of reducing the weight so that you can still meet the requirements for flight. And this was an example of a static test. Beyond that, when you start thinking about putting aircraft into production or even looking at larger size airplanes, you also need confidence in the models that are used to simulate what is happening in the actual physical test. So finite element modeling is very important to improving that understanding, particularly if you're interested in putting something into production. You don't want to have to do a large number of static tests, but you would rather have confidence in your model matching the static test of the sacrificial part. One of the other questions that we wanted to answer, now that we had explored methods of how to improve the strength of 3D printed parts, was how big of an airplane can we build using the limitations of the existing materials? And this was a study looking at the different possible options for increasing the size of the aircraft, limited by the root bending moment, which is the integration of the lift along the wing. And so the answer to the question is really that it really depends on what the airplane is designed to do. Most large airplanes that are long endurance airplanes are designed to be somewhat of high altitude, long endurance aircraft, the HALE UAV that you've seen certain entities pursuing. But they're really designed against the structural limitations of the material being used in the wing. Another alternative is that you can design much lighter weight structures that have some docking feature, where there's minimal load transfer between individual components, but they can still share information. A good example is of sharing of actual physical material is air-to-air refueling. If an airplane is refueling from a tanker, for instance, there's minimal load transfer, but still the physical fuel is being transferred. And so I think this is really has a great potential to produce aircraft that are just as efficient as some of the HALE UAVs, but are extremely lightweight in their design. And this is an unexplored area. Another question that we had to answer related to the strength of the part is how would that part survive in a crash landing? And so we did catapult launch tests, which are shown here, where the aircraft is launched with 20 pounds of weight loaded into the center fuselage to simulate a much larger airplane. And as you see in the test, the airplane just breaks apart, which is great. It confused some of the students at first because they didn't know whether it should be thought of as a failure or a success. But for us, it was a success because we learned more about our launcher system and we gained confidence in the ability for that launcher system to handle larger airplanes. And so this is an example of some of the information that we got from our catapult launch testing, where the accelerations for the launcher matched those that we needed to launch much larger airplanes. And we went through many different iterations of that. So now going to flight, we take our simulations and then we try to learn something from the flight testing to calibrate our simulations to the actual data that we collect in flight. And so this is one of the first flight tests. As you saw previously, it was a little rough coming off of the catapult launcher. But luckily by that time we had de-risked the launcher design itself, so that the real worry was how the airplane would perform in flight. And this was some video that was taken. We're located in the right corner over there on the ground as the airplane's flying by. And then the question was, now that we have a better understanding of how the airplane performs, can we understand and map the aerodynamic improvement to the models that we've been generating? And by doing that, we can now start to build a way of the computer or the laptop that's being used as a ground station to directly control the aircraft instead of having an RC pilot fly the aircraft. So this is known as autonomous flight, where we want the airplane to be flown by the computer instead of by a pilot. And so we can do certain experiments with waypoint navigation, where we set up the flight path in the software that the airplane is going to take. And these are actually the actual coordinates of the airplane as it's following that flight path, which has been set up. So this is an example of how we took that design, which we now had a better understanding of how it flew and how efficient it was, to an autonomous flight test. One of the final considerations I want to mention here is that the useful life of an airplane depends also on how it's being used, and we often refer to this as being the dynamic loading environment of an aircraft. We tend to think that the more material we add to an airplane, the longer life it will have, but this is kind of counterintuitive to what we see. Airplanes that are usually designed to a higher safety factor, meaning more weight is put in the wing, degrade very quickly because they operate in very extreme environments that put certain stresses on the materials. We can also compare what we see in the aircraft design world to what we see in the natural world with bird flight. And surprisingly, some of the most long endurance performance birds like the albatross are ones that live the longest. So maybe that gives us some lessons about how we should also be more conscious of our health and what type of stresses we have in our bodies to live as long as we can. Finally, I'm going to end up with summary and conclusions. So the key elements that made this project a success were that we were able to leverage open source avionics, we were able to leverage modular design reuse of the Dragonite components, and rapid prototyping provided to us through the facilities available in the NASA Space Shop. And we were also able to leverage the use of the Airworthiness Flight Review Board that is located here at NASA Ames, which walked with us every step of the way through our flight testing process. And by taking advantage of these three core elements, we were able to achieve flight in less than 8 weeks. This is less than 2 months, going from a paper design all the way to the final flying autonomous flight. And not only did we do it one time, we did it twice. So this is an example of some of the 3D printed parts that we came up with, some of them using the lattice type designs. This design was done by Kenny Chung, who is a researcher here. And we also were able to take an existing wing that was made out of pink foam and recreate it using 3D printed parts. This is essentially the idea of 3D printing a fuel tank, where the airplane can be, the parts can be designed so that they fit together in a way that you just simply add fuel in the middle of the wing, and you can snap it on your airplane and go and fly. And so this was a major contribution, I think, in the area of the wing design using 3D printing. And as I mentioned before, concept to flight, autonomous flight in less than 8 weeks by leveraging the elements that I showed earlier. And so we want to, so this was an extremely successful project from my perspective. The team members that contributed and the mentors deserve all the credit for this, and I'm just their spokesperson. But some of that success was reflected in the media coverage that we received. We had a very interesting Halloween article that was published with referring to how we were able to take these airplanes and put them together almost like a Frankenstein monster. And one of the other interesting insights that I derived from this project was that in the course of 8 weeks, these student teams all came up with solutions very different to the same problem. And if you take all of those, the three solutions, and you superimpose them, you get something that you may have seen on the way in, the superimposed Franken-Eye. So the ironic thing about this design is that it looks very similar to a Russian design, actually, that currently holds 15 world records. Very different scale, very different application. But the point is that by using the rapid manufacturing and rapid prototyping approach, we were able to kind of start focusing down on the elements that were most important for improving performance. And now we were able to generate a design that we would expect to be an optimal performer if it, say, were scaled up to a larger size. And we also were able to, I was able to meet President Obama on one of his visits, and I'm very grateful for the support that was provided with his visit. And the final comment was that in one of our articles, we're actually given a new word, Frankenstein, which I'm really happy about. And I think people just get the idea that we're trying to reuse, we're trying to repurpose, we're trying to recycle existing components, but just re-architect them in a different way that improves their performance. And we've also seen that aviation industry has taken some interest in this. These are some examples, recent examples, of how 3D printing and modular design are being used in different ways. And we only expect the future to be much brighter in these areas, and the potential cost savings is going to be reflected as we see some of these methods potentially applied to larger aircraft systems. I would say that this area is an emerging area that needs more research, it needs more attention, but it has the potential to really impact the industry in a big way. So with that, I will, With that, I will ask for your questions. The next slide is just a, yeah. With that, I will ask for your questions.
So if you have questions, please line up on the microphone in the center aisle and ask one question only.
Hi, and thank you for the lecture, very interesting. I was wondering if there's any crossover with other industries that could clearly benefit from the whole modular design idea. In other words, like buildings or automobiles or subways. Has there been any sharing of lessons learned, et cetera?
Yeah, thanks for the question. We see modular design all around us. Almost every assembly or complex system that we deal with on a day-to-day basis has many components. But typically, those components are just added together using screws or bolts or in different ways. I think the thing that is unique about this specific design is that we approach aircraft design from the perspective that parts have to be interchangeable. We want simple interfaces, mechanical and electrical interfaces, to make plugging in a new part just as simple as plugging in a device into a USB drive on a computer. And so I think we can leverage lessons learned from other industries like the computer industry and like many of the other industries that produce these complex systems that have multiple parts.
Hi. I had a question about scaling that you touched a little bit on. So there's a big difference in material properties between what you can 3D print and what traditionally is used in big airplanes. So I imagine that as you go smaller, those kinds of restrictions get easier to deal with. So did you guys come up with any kind of estimate on how big of an airplane or what kind of wing loading or some other metric that you can reach using these kinds of approaches?
So you bring up some very important points. Large airplanes specifically are in a class of their own because they use parts that are extremely strong and lightweight. For the purposes of this project, we were really focused on unmanned aircraft because we saw that as the low-hanging fruit, because we weren't putting people's lives at risk by flying an unmanned airplane. I think as the materials that we see in 3D printing improve and become stronger, which we expect they will, we can then start to scale up to larger sizes. One of the aircraft that we simulated in some of the results that were shown was actually looking at a 16U design based on the Dragon Eye concept, and it was approximately a 60-foot airplane. So at that span, there are also other questions that need to be addressed, like how do you control it, how do you launch it? And we think this is just the very beginning of where it's going. I hope that answered your question.
Hi, I have a question about the additive manufacturing and the modular design combined. I assume there's some type of efficiency loss for the structural mass when you look at adding parts together at the joints. Can you comment as to what type of degree of efficiency loss you get by using a modular design?
Right. So one of the things that is worth noting is when you look at aerodynamic efficiency of aircraft, it really, aerodynamic efficiency can be achieved in many different ways by using biplane wings or using non-planar structures. What really matters in terms of aerodynamic efficiency is what the lift distribution looks like across the configuration. And we often account for what that lift distribution looks like by looking in the thrust plane, which is actually several spans behind the airplane. So from an aerodynamic efficiency perspective, we can achieve similar performance using modular designs that have structurally weak parts. But from the structural efficiency perspective, the design of the joints can be extremely important for the application that is mentioned. In one of the earlier charts I showed, a self-docking structure can be designed to have very weak joints, but it just needs to hold the position required to maintain the aerodynamic efficiency benefit. That's just an example. But typically what we see in most high-altitude airplane designs is that those designs are really pushing the limits of the structure. And I think there are opportunities that perhaps don't push the limits of the structure, but more focused on the control challenges.
Thanks for your talk, Kevin. Could you talk a little bit about how you would tune the control laws for these planes, given one design or the other?
Right. So for the purposes of our project, which was on a short time scale, on a two-month development period, we used open source simulation hardware, Mission Planner and X-Plane, to simulate the flight performance of the aircraft. And those software tools allow us to build a virtual flight dynamic model of the design. In a more rigorous, for more rigorous design, we would actually go into calculating stability based using stability derivatives and those type of things. But for the purposes of our experimental project, we relied on the flight dynamic model being created by the flight simulator.
Please join me in thanking Kevin Reynolds for an excellent seminar.